towards complete icon labeling in mobile applications. As the second most frequent UI type, icons expose important functions of mobile apps. However, icons are not accessible by their nature and require developers to add labels. Existing research indicates the severe accessibility issues of missing labels. Over half of clickable icons are unlabeled, and over 2/3 of image-based buttons are missing labels in 77% mobile apps. There are two common methods to add missing labels for icons. Using crowdsourcing, humans can provide labels even for uncommon icons. However, it is error-prone and time-consuming. Using machine learning, image classification can classify common icons with low latency. However, it may not handle less frequent icon types. Our work also uses machine learning techniques to generate labels for icons. The goal is towards more complete coverage of icons. Here are two main contributions of our work. First, an analysis of our dataset of more than 300,000 icons from iPhone apps, identifying a highly uneven distribution of icons. Second, a pixel-only method that generates icon labels by classifying common icon types, identifying long-tail icon types, leveraging nearby tags, and recognizing modifiers. Our method covers 99.5% of collected icons. We get icons from a large-scale iOS app UI dataset in our previous experimentation work. From screenshots, we extracted 338,000 icons using the UI type annotations. Using this annotation interface, crowd workers provide labels to icons. We defined about 90 common icon types based on previous research. For each icon, annotators determine if the icon belongs to a common icon type. Some icons do not belong to predefined common icon types. We use a semi-automatic method to explore them in 5 steps. First, cluster the icons by pixels. Second, compute keywords for each potential cluster and merge clusters with the same keyword. Third, assign icons to a cluster if the distance between the icon and the corresponding cluster centroid is less than a threshold. Fourth, repeat step 1 to 3 until a convergence. And finally, let workers verify the clustering results. After annotation, we run analysis on icon type distribution. Our dataset contains 98 common icon types and 331 long-tail icon types. Some app categories have a higher percentage of long-tail icons than other categories. As shown in the figure, the highly uneven distribution across icon types resembles a long-tail distribution. After manually examining icon dataset, we observed that the semantics of icons are relevant to many factors, including their basic shapes, nearby text, modifiers, and other contextual information on the screen. After data analysis, we decided to create labels for both common and long-tail icons and recognize nearby text and its modifier symbol as additional context of icon label. Here is our system flowchart. Given a UI screenshot, an object detection model first locates all icons. Then, a model classifies if the icon is one of the common icon type. Otherwise, the icon will be sent to long-tail icon classification model. Crowdsourcing is a backup method if both models fail. In addition to icon type, our nearby text detection and modifier identification modules provide additional semantics of the icon. For the common icons, we use ResNet 50 to perform image classification task. We use focal loss to handle the class imbalance by downweighting the well-classified examples. If an icon is classified as long-tail, it will be sent to our long-tail icon classification model. To avoid overfitting issue due to uneven distribution of icons, we use a few-shot learning method for long-tail icons. Prototypical network can classify the icon types given a few examples. For each icon type, we will sample several examples as support icons, and then use a backbone model to extract features from these support icons. We then obtain a prototype for each icon type by calculating the mean features of support icons. Then, we can predict the label of a query icon. We obtain features of this icon, find the nearest prototype, and assign the label. This method can be generalized to new icon types by adding a few examples. We first evaluate models on icons cropped by annotations, which have very accurate bounding boxes. Our common icon classification model achieves 96.3% accuracy, and the long-tail model achieves 78.6% accuracy. Then, we perform an end-to-end evaluation on icons cropped by UI detection results on screenshot. Our system still achieves similar accuracy, which indicates our model are robust to less accurate bounding boxes from UI detection results. One potential application of our work is accessibility. In this example screen, our method recognizes more icons than previous work. Higher coverage of icon types will further support screen readers to recognize icons without label and improve app accessibility. Here are some limitations of our work. The same icon may have different meanings under different contexts. Our system can be further improved by considering the additional contextual information in the UI. Currently, we directly concatenate nearby text and modifier labels. Future research may find better ways to integrate them to create more concise and accurate labels.